In this video, what I want to focus on is the drawing of Lewis structures. The single most important thing to remember and to be able to do easily from general chemistry is to be able to draw good Lewis structures for covalently bond molecules. To draw a good Lewis structure, you don't know what the molecule looks like, and if you don't understand what the molecule looks like, you are not going to be able to figure out how molecules are going to interact with each other. You need to know where the electrons are, you need to know where the electrons aren't, so you can get places that have high electron density together with places that have low electron density. So you need to remember the rules for drawing Lewis structures. In fact, we're not really going to draw Lewis structures because Lewis structures use pairs of dots to represent pairs of electrons. And we're actually going to use lines. Strictly speaking, that's a Kekule structure, not a Lewis structure, but we use the terms relatively interchangeably. And so the best way, I think, to go through Lewis structures is to do kind of the stepwise process and apply it to several molecules at the same time. So let's look at HF, hydrogen fluoride. Let's look at PCl3, phosphorus trifluoride. Let's look at CH4, methane. And let's look at carbon dioxide. And carbon monoxide. And let's look at NO3 minus, which is the nitrate. Hopefully you remember all of those names. Hydrogen fluoride, of course, is a gas. Hydrofluoric acid, when it's dissolved in water. CH4, methane, C2H6, ethane. Hopefully you remember the prefixes for the first several hydrocarbons. And then CO2 and CO, carbon monoxide and carbon dioxide, are products of burning methane in the presence of oxygen. So what's the first step of drawing a Lewis structure? The first step of drawing a Lewis structure is always to figure out how many electrons you're working with. You need to count the number of valence electrons. Which of course presupposes that you remember what a valence electron is. Okay? And hopefully you do remember what a valence electron is. The valence electrons are the electrons with the highest principal quantum number. Largest value for n. And since we're pretty much only working with elements that are in the second and third row and hydrogen, which is in the first row, we're going to be working with the electrons that are in the s and the p orbitals. Because as you go down to the fourth row, the transition metals start filling the 3d. That's not the highest value of the principal quantum number. They are outer electrons, right? Because the outer electrons are all the electrons that are put in after the previous noble gas. But they're not valence electrons because they have a lower principal quantum number. And so if you were to go down from phosphorus to arsenic below it, it would have 4s and 4p electrons. Those would be the ones you'd be counting. You wouldn't count the 3d electrons that go into the transition metals. They're not valence electrons, they're only outermost electrons. So if we count the number of valence electrons, we know that hydrogen has 1, and we know that fluorine as a halogen has 7. Hydrogen fluoride has 8 valence electrons. We know that carbon has 4, and each of those 4 hydrogens has 1. So again, that one also has 8 valence electrons. We know that phosphorus has 5 valence electrons, and chlorine has 7. So there are a total of 26 valence electrons for phosphorus trichloride, PCl3, Carbon has 4, oxygen has 6, 16 total electrons. Carbon has 4, oxygen has 6, 10 total electrons. Hydrogen has 5, each of the oxygens has 6. And then we also have to add an extra electron for the negative charge. 4 total electrons. 4 of the molecules that I've put up on the board have a multiple of 8 as the number of valence electrons. When we have a multiple of 8, it typically means that there won't be any lone pairs of electrons on the central atom. When we don't have a multiple of 8, it often means that there will be a lone pair on the central atom. So when the number of valence electrons is a multiple of 8, there will generally not be lone pairs central atom. The lone pairs will generally be on the outer atoms. If you get this step wrong, and you count the wrong number of valence electrons, everything will be wrong. Right? There's no partial credit. If you don't have the right number of valence electrons, you're not going to get any points on anything. The second step is to choose the central atom. Right? We need to pick a central atom. Talked about how there won't be, well, we need to know what the central case is, the least electronegative atom. Which generally means it's the atom that's furthest to the left and closest to the top. Sorry, closest to the bottom. Furthest to the left and closest to the bottom, because the electron generally decreases as you go from top to bottom. So the least electronegative atom. The exception is it's never hydrogen. Because hydrogen can only have 2 electrons around it, a filled duet as opposed to a filled octet, hydrogen is never going to be the central atom. So in the case of methane, hydrogen does have a lower electronegativity than carbon, right? Carbon is 2.6 and hydrogen is 2.2, but carbon is going to be in the middle because hydrogen can be. So in this case, there is no central atom, right? It's a diatomic. Same with carbon monoxide. There's no central atom to worry about. But in the other 4 cases, we have to worry about a central atom. And the central atom will be carbon here, simply because it can't be hydrogen. Phosphorus has a lower electronegativity than chlorine, so it will be phosphorus. Carbon has a lower electronegativity than oxygen, as does nitrogen. And you'll notice that when we're drawing simple binary compounds like these all are, generally we write the least electronegative atom first, and so the central atom is often the first atom. But that's not a good assumption, right? It's not always going to be the case. It is always going to be the case that it's the least electronegative atom, unless it's hydrogen, right? And you'll see that in hydrocarbons where carbon is the central atom. You'd also see it in ammonia, NH3. Nitrogen is significantly more electronegative than hydrogen, but hydrogen can't be in the middle, so nitrogen has to be. Once we've picked the central atom, we're going to form a single bond to each other atom using a pair of electrons. So we will put the hydrogen and the fluorine together using a single bond. We'll put the carbon here, and we'll form a single bond to each of the hydrogens. We'll put the phosphorus in the middle, and we'll form a single bond to each of the fluorines. Put the carbon in the middle, form a single bond to each of the oxygens, nitrogen in the middle, forming a single bond, each between oxygens,